Good evening, Ormskirk.
Good evening.
A pleasure to be here to tell you about astrophotography. And as you can see from the subtitle, the emphasis is going to be on photographing the universe, but without ridiculously expensive equipment. Along the way, I will tell you a little bit about the ridiculously expensive equipment, but then I'll tell you how you can do it on an altogether smaller budget. So I'll be talking about starting simple and then looking at what equipment that you might conceivably want to buy and why astrophotographers buy particular equipment. And then I'll be looking at cameras and star trackers. I'll be explaining what a star tracker is in due course. And then I'll use this evening as an excuse for showing a whole load of images that I've been taking over the years. And that will continue with just a tiny amount at the end there, talking about going on safari to very dark skies and looking at the skies there. So starting with what you can do basically with nothing except a camera and a tripod. This is a very old image taken quite some time ago. Where possible, I've indicated the circumstances at the bottom there, so you can see that this was back in the days of analog film before going digital. And this was take the camera, put it on a tripod, point it at the sky and expose for about 5 minutes or so. I'm not actually sure whether it was 5 minutes, except that we can see that the stars have trailed because the Earth rotates roughly once in 24 hours. And so you can work out simply from calculating how far the stars have trailed, roughly what the exposure was. So right in the center there, there's the North Star Polaris, which hardly seems to move. It's not actually at the North Pole, it's just very close to the North Pole, the point that the Earth's axis points to. And so that star hardly moves at all and so gives you virtually a point, whereas all the other stars appear to move, and the further from Polaris, the longer the trails get. You can see already that it's quite an aesthetically pleasing image, especially when you realize that actually you start to pick up some of the star colors when you do a trail like this. Moving on to digital photography, there's no reason why we should be restricted to just a few minutes. And with digital photography, we don't necessarily want to hold the shutter open for 6 hours, approximately 6 hours here. You can see the stars have done approximately 1/4 of a revolution. With digital photography, we can take a large number of shorter exposures. And that's generally how all astrophotography is done, not simply for star trails. For any astrophotography, why take one long exposure when you can take a lot of short exposures, which gives you a number of advantages, not least if one of the short exposures gets spoiled by a passing aircraft or a passing satellite or even passing clouds. You can throw that one away and use the remainder. In this particular case, 360 images, each of which was 1 minute, and then software will allow you to put them all together to make these star trails. So yes, it was taken at night, even though it looks like daylight. The white observatory buildings here and the grass in the foreground makes it look like daylight only because there was a full moon in the sky, which is why the sky is blue, not black. And we have here the ability not only to use software to make the stars trail, we can, if we wish, use free software to actually make a movie of the stars rotating around Polaris, or I should say, apparently rotating around Polaris, because of course it's the Earth that's moving, not the sky. So software is available. I can point you to free software if you so wish, if you want to have a crack at this sort of thing yourself. There's a certain amount of astrophotography is simply being in the right place at the right time. For instance, a total eclipse of the sun, you can't just click your fingers and hope that this is going to happen. Effectively, you have to travel to the right part of the world where the alignment of the moon and the sun is such that the moon will just cover the sun. So in this particular case, I wanted to go somewhere that was almost guaranteed not to be cloudy. So some friends and I went to the Sahara Desert to actually see this particular spectacle. The beautiful corona, the atmosphere of the sun, which effectively is only visible once the glare of the sun has been removed by the disk of the moon. Similarly, right place, right time is catching the aurora borealis here just north of the Arctic Circle, around the Arctic Circle in Iceland. If you go at the right time of year, and if you're lucky enough not to have any clouds, you can get spectacular displays of aurora, huge curtains of light that stretch tens, if not 100 kilometers into the sky, shimmering and almost as if they were fluttering in the breeze, these curtains. And the shapes and the changes and the dancing of the lights is absolutely mesmerizing. You can still see some of the constellations in the background. In some cases, the aurora is so bright you can hardly see the stars through the aurora. The sun is quite active at the moment, which means it is possible to catch the aurora further south than the Arctic Circle, but generally speaking, you don't get anything like the displays that you would get from going to much more northerly latitudes. So here's a picture from my bedroom window. You do pick up some of the colors using a camera, but effectively you can't see anything. Even when the aurora are, quote, visible, unquote, from the UK, you can hardly make out the structures that you're supposed to be able to see, even though the sensitivity of modern digital cameras does allow you to pick them up. So let's think about if we wanted to do astrophotography, not simply camera on tripod, take picture of the sky. What if we wanted to be a little more ambitious? Let's face it, it's an awfully big universe. There's a huge number of targets out there we can photograph. Why limit yourself to only photographing things on Earth when there's an entire universe out there? What sort of telescopes or mounts or equipment might you think about buying? You could ask, what's the best telescope to buy to give me the best images of the universe? Well, I guess the answer is probably the Hubble Space Telescope. It is now 35 years old. It was launched in 1990. 35 years on, it's still producing wonderful images, but they are going to retire it before too long. So just keep an eye on eBay because, okay, buyer has to collect it, yes. But apart from that, so if you've got $1 billion or $2 billion to spare, then go get yourself a Hubble Space Telescope and you can get fantastic images of galaxies and the famous pillars of creation in a nebula in the constellation of Serpens. So that's a bit unrealistic. Most people haven't got $1 billion to spare. So you have to downsize your expectations somewhat. If you can't dig quite that deep, if you've only got 100 million or so, I guess that might apply, this 747 has just been decommissioned. There's a telescope in the back there, which is why there's a big hole in the fuselage. This is an infrared telescope in the back of a 747 operated by NASA. It's called SOFIA, the Stratospheric Observatory for Infrared Astronomy. The idea was infrared light gets absorbed by the atmosphere, so you fly above as much of the atmosphere as possible. At 10,000 or 12,000 or 14,000 meters, you're above an awful lot of atmosphere, and so very little is absorbed by the air above you. That is now decommissioned. So again, I'm not sure what's happened to the 747, but if you fancy a 747 with a telescope in the back, again, watch out on eBay. If you've only got £1 million or so, if you're a real pauper, then there are other telescopes, for instance, the Liverpool telescope, which is not in Liverpool, but is in La Palma. These are large robotic telescopes. You don't have to go to La Palma to operate it. You can effectively operate it over the internet and again, produce nice images of either pillars of creation or that galaxy again called Messier 51. Now, most amateurs, of course, don't have that sort of money. And when it comes to amateur telescopes or amateur equipment, well, if you use the cliche, the prices can be astronomical. So telescopes might start from a few £100 or so, but there's really no upper limit. Some amateurs still call themselves amateurs if they buy telescopes costing 10 or 15 or 20 or 25,000 pounds. So it depends how enthusiastic you are in terms of observing or photographing the universe. There's a bewildering number of types of telescopes. That's not a big selection. If you get a telescope catalogue, you will find possibly 1,000 different telescopes of different designs, different specification. So it is very confusing to try and work out what would be a good telescope if I was interested in getting one in order to photograph the universe. Some amateurs will start with a telescope like that and then they'll decide to turn it into tech spaghetti by buying as many different add-ons as possible, like cameras and bits and pieces and little mini computers, etc. And they will try and turn it into something akin to an absolute rat's nest of cables. Some people simply like to have a telescope as a toy, not necessarily something they can use or produce images. It's one-upmanship, saying, look how many cables I've got on my telescope. That's going one up with the Joneses. One thing to bear in mind is that anybody that's serious about astrophotography will tell you, yes, if you're going to buy a telescope, you want one of a good optical quality. You appreciate that as photographers, that the quality of the lens produces the image. But remember, we live on a moving planet. The Earth is rotating, and therefore anything in the sky is going to be apparently moving around the North and the South Pole. And many serious astrophotographers would say, spend at least as much attention and possibly at least as much cash thinking about the mount on which the telescope is placed, as well as the telescope itself. Don't simply get the best set of optics you can and then put it on a really wobbly tripod, in which case you'll never be able to follow the sky and take pinpoint images of the stars and the galaxies and the nebula that are out there. So there are manufacturers who will provide very stable, very accurate, very precise motion, such that you can counteract the motion of the Earth in order to point your telescope at a particular object and have it effectively locked on, rock solid. So yes, it's definitely a good idea to use the most sturdy and most precise mount that you can. But you can look at that and say, well, yeah, that's fantastic, but is it really worth $10,000 to give me a really rock-solid mount for my optical equipment, whatever it's going to be, my telescope and my camera, etc.? So I would suggest, if anybody is in the least bit serious of thinking about getting into astronomy and buying a telescope, don't jump in with both feet until you've had a serious think about it or talk to somebody who can advise you as to what's the best way to get started, what's the best entry level. If you're serious about astrophotography, what would be a suitable telescope to do the job? And not surprisingly, that's a different talk that I can give. So if you did decide to buy a telescope, where are you going to put it? Well, that's one place you can put it, in a beautiful observatory in the middle of a national park, like here on Palomar Mountain, California. I visited that back in 1982. I think I've actually changed my shirt since then, which is excellent. Okay, so 1982, I was still a student. I visited this observatory dome thinking, this is fantastic. The world's biggest telescope was in that observatory dome. I figured when I grow up, I'm going to buy a house with a back garden big enough for a telescope dome like that. Okay, I had to downsize my aspirations slightly because in 1998, I went out and bought a B&Q shed, converted it so that the roof was removable and had a sort of a shower cap, a tarpaulin over the top, which could easily be removed to allow me to see the sky from inside. You can tell this is quite old, not from the age of the telescope necessarily, but the fact that the laptop looks like a brick rather than the very slim laptops that you get these days. And with a telescope in your back garden, that's great because you can effectively say, oh, the skies are clear, walk into your back garden, open it up, and then you can observe the universe. And you can eyeball and you can photograph. For instance, even our closest neighbor, the moon, we shouldn't overlook the fact that just because it's there half of the time, we don't always notice it during the day, but of course it's around for about half the time. Our closest neighbor can be fascinating. Just watching the changing craters as the sun angle changes, and that changes what you can see of the detail on the surface of the moon. Photographing the moon through a large telescope, eyeballing it and photographing it can show incredible detail. And I wasn't quite sure whether or not all of the detail would show up, so I decided to zoom in for you a little bit. That's a very flat crater there. This is Mare Imbrium that's filled in this particular crater. That large crater is Copernicus. And you can see incredible detail in the craters. There's also what looks to be a hair on the surface. That's not a hair, that's actually a shadow caused by a fault line where the surface of the moon has fractured and faulted, and at certain times of the month that produces a shadow that you can see there, a so-called straight wall. So the amount of detail that you can see on the moon is such that even though it's a, as it were, dead world, Every time you look at it, you're looking at it with a slightly different angle of the sun, so the shadows are always different, and so the amount of detail that your eye can pick up in the mountains and the craters, etc., is slightly different every time you look at it. But the real beauty of a telescope is if you can do astrophotography of not just something local like the moon, but something much further away. For instance, here's the Pillars of Creation yet again. I took this image last year, 2024, and this is taken through a not particularly cheap telescope. And by not particularly cheap, I mean you can't get one of these telescopes for hundreds of pounds. You would have to spend a four-figure sum to get a telescope that would allow you to take an image like that. So this is a stellar nursery. This is where stars are being born. The Pillars of Creation are called that because these are gas pillars that are being sculpted by stars that have only just been born inside these pillars themselves, born out of this large cloud of hydrogen, which is glowing pink, because hydrogen gas glows pink when it's excited. When a star gets to the end of its life, it might look like this. So our sun, in a few billion years, is going to expand. It's going to be quite a while before it starts to do that, don't worry. But in a few billion years, our sun will expand, and the outer layers of the star are going to be shrugged off and produce a nebula like this. And that right in the middle there is the core of the star that originally shrugged off these outer layers. Pink and blue, characteristic of the light that glows from hydrogen and oxygen. So we can tell what this is made of just by looking at what color it is. And so this is pretty much what our sun is going to look like in another 5 billion years or so. And again, another nebula in this particular case, a lot of hydrogen here producing this characteristic pink glow. Some of the light is being absorbed by these dark regions, which is why you get these dark filaments in front. And just like on Earth, when light travels through the Earth's atmosphere, it gets scattered by the air and our sky is blue. So some nebula are blue for the same reason, because the starlight is getting scattered. And so you get this beautiful contrast of colors in lots of these nebulae that exist. And I might add that in these particular images, I'm not using filters. It might be a good idea to use filters. That's another subject, I guess. But all of the images you're looking at this evening are not using filters. So these are the genuine colors. As best we can tell, these are the genuine colors of these various objects. As I say, the colors are characteristic of what chemical elements are actually producing these. So it's not cheap to produce images like this, because you have to spend essentially thousands of pounds on a telescope in order to get these images. And this is definitely not cheap as well. Don't ever try this unless you know what you're doing. It is possible to take pictures of the sun, but only with specialist solar telescopes. You can always project an image onto a piece of paper and photograph that. But if you want to get this sort of detail on the face of the sunspots, these filaments, these huge plasma prominences that are erupting from the sides of the sun here, you can only get that sort of level of detail by buying a specialist solar telescope, which is safe to use despite the enormous amount of light that's coming from the sun. If you want to buy a telescope that's good for nighttime use, they generally start at hundreds of pounds. But telescopes that are dedicated for looking at the sun, they don't even start until you get to well over £1,000. So these things are not cheap. Again, it's absolutely fascinating to see how the sun changes, not simply from day to day, but virtually from hour to hour, sometimes minutes from minute. You see these huge plasma eruptions on the surface. Bear in mind that the size of the Earth to scale would be approximately the size of one of these tiny dots here, roughly speaking. So these prominences are way, 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 way bigger than the size of the Earth. So unfortunately, a very expensive way of doing astrophotography. And yes, it is astrophotography, even though it isn't taken during the night, because astro means star, and our sun is a star. So that counts, as it were. So I've told you the expensive way of doing it. The cheap way of doing it is don't do anything but plonk your camera on a tripod. The expensive way of getting really nice images of the universe is to go out and buy yourself loads of technical equipment like expensive telescopes and very sturdy mounts that allow you to effectively derotate the Earth to take into account the fact that the skies appear to be moving. But there is a way of doing astrophotography without ridiculously expensive equipment, which is what I want you to take home as the message this evening. So I'm talking about cameras mounted onto star trackers. I'll come to trackers in just a moment, but first just a reminder of how cameras work. I'm sorry if I'm talking to a photographic society, you probably know all this, but just a reminder that back in the old days when we had monochromatic film, or indeed a monochromatic digital camera such as a CCD, then the light is focused onto the monochromatic surface, the monochromatic sensitive surface, whatever it may be, analog or digital. And if we want to take a color image, well, we would take 3 images in turn with a red and a green and a blue filter somewhere between the lens and the film, usually, or the other side of the lens. Now, if we want to take a color image, we either say, well, we've got a monochromatically sensitive emulsion or chip, and we can use individual filters. Of course, it wasn't too long before the filters were actually embedded into the emulsion to give us color film, either color print film or color slide film. But with CCDs, we are still using monochromatic CCDs. All cameras technically are black and white cameras, but they simply have the color filters applied to the surface of the CCD. If we have a look in detail at what's going on the surface of a chip, which is in essentially any digital camera that you've got, there will be a grid of color filters. They won't necessarily look like that, but that's a very common way of laying out the filters on the individual pixels of the CCD. So when the camera takes a picture, what it actually takes is picking up information about the red, the green, and the blue channel, and the computer that's on board, either your phone or your camera, whichever camera it is, the computer is then responsible for taking the red, green, blue information and combining it to give you a color image. But bear in mind that technically the CCD is not a color sensitive thing. It's only relying on the filters on the front. That's true regardless of whether we're talking CCDs, charge-coupled devices, or whether we're talking about CMOS, complementary metal oxide semiconductor, a different technology, but the same basic idea as to how images are obtained. I thought I'd just do that as a reminder of the difference between color and black and white, because when it comes to, I'm interested in astrophotography, I want to buy an astro camera, then you have a number of choices. There are relatively low resolution cameras that will start at maybe a few £100 or so, maybe a couple of £100. If you want higher resolution, you have the choice of either getting color cameras or mono cameras. And it might be surprising to realize that, for instance, I've just picked as an example 7 megapixels. The cost of a color camera and the cost of a monochromatic camera are pretty much the same, regardless of whether from the same manufacturer. Even the same manufacturer, if they're producing a color version of a camera and a mono version of the same camera, they will often sell them at exactly the same price. You might assume that the color one would be more expensive because it's more complicated. In fact, the extra manufacturing required to put red, green, blue filters on top of every pixel, the extra manufacturing cost to do that is essentially zero. If you're going to make a CCD, the extra that you do of putting the filters on as the last layer really doesn't make any difference. And so they don't bother putting them at different price points. If you did want to buy yourself a mono camera, then you might want to use filters if you wanted to generate color images. And you can buy filter wheels, called, for obvious reasons, filter wheels, because we've got a filter in a carousel, as it were. And in the old days, those used to be moved by hand, but these days they're moved by a little motor, which is controlled by the same computer that you're using to take your images. So you can specify that you want the camera to take an image, and you can specify the filter wheel to rotate and put a given colored filter in front of your sensor. This has the advantage that not only have you the option of saying, I want to have a red, green, blue filter to take color images, you also have the option of saying, I want to put in a specialist filter. I wanted to put in a filter that only lets the light of hydrogen clouds through. I only want to let through the light produced by oxygen that's glowing. I only want to let through the light that's produced by sulfur. You can specify which particular element that you want to actually image, not simply show me everything that's red, everything that's green, everything that's blue. And that's why some people choose a mono camera, because you have much greater control as to what it is you're going to be imaging in terms of what light you're going to let hit the sensor. But of course, that just adds yet more cost. Don't take these prices as gospel. They're just almost random prices that I pulled out as an example. But if you did want to buy yourself a filter wheel, it would cost many hundreds of pounds in addition to whatever you're paying for the camera. So you might end up spending thousands of pounds on a telescope and thousands of pounds on a mount and thousands of pounds on a camera. This is why I say it starts to get ridiculous. It doesn't take long before you've added up a whole load of kit that is very close to £10,000 if you want to be serious about this. But the direction I'm coming from is, yeah, I've got nothing against anybody that's got deep enough pockets to want to do that. But what if you've already got a camera? Which is why I'm talking to a photographic society, not an astronomical society. I'm guessing that a number of you will already have a bridge camera or a DSLR camera or a mirrorless camera or something else. If you've already got a camera that you're happy with, why would you want to go out and spend shed loads of money on dedicated astronomical cameras? Yes, they are fantastic pieces of technology, but maybe you've already got a fantastic piece of technology and you're using it to take a picture of your family or your dog or the trees or landscapes or whatever it is you're photographing. And that's what I decided to do some years ago. Although I've had a telescope in my back garden for a long, long time, I got really interested with, yes, but I've already got a camera. What can I do with that without bolting it onto a telescope? So a tracker is any mechanical device, usually mechanical device, that will derotate the Earth. As the Earth spins once in 23 hours, 56 minutes. If you can arrange it so that your camera spins in the opposite direction at a rate of 1 revolution in 23 hours, 56 minutes, and it's spinning on the same axis, so if the Earth's axis is spinning in that direction, you arrange it so that your tracker will spin your camera in the opposite direction on the same axis. That means that your camera, as far as the universe is concerned, your camera is static. And therefore you can point it at a particular object in the universe and it's not going to trail like those stars that we saw in the first two images. I decided to build myself a tracker back in the heady days of, when was it? 2007. Gosh, what a long time ago. I built it, you can see, from bits of aluminium and a couple of AA batteries and a little motor bolted onto the bottom and a couple of door hinges. It'll cost you a few tens of pounds depending on whether you already have these things lying around in your garage or not. And if you are interested in building yourself a star tracker, that's how you do it. I've printed it out here. So I built that and used it, took it on holiday, took it to Africa, got a few eyebrows raised as it went through the X-ray machines. But I took it to Africa and took images with it. After a while, after quite a few years, I decided to switch to using a commercial tracker. So that one I built myself, which was great fun. And one of the reasons I built it myself was because at the time, back in the noughties, back in sort of 2000-ish, very few manufacturers built trackers. In other words, there were plenty of people who built telescopes and big, expensive mounts to mount those telescopes. Very few manufacturers built relatively cheap trackers. These days, there's lots. There's at least half a dozen different manufacturers who build trackers. And remember, a tracker is effectively just a motor in a box. It's a little bit more complicated than that. This particular one that I opted for back in, 10 years ago now, so I've been using this one for the last 10 years. It's a tracker on which you bolt the camera to this plate on the top, and this is a little telescope, a little polar scope, just to make sure you're lined up correctly with the axis of the Earth. Remember, the axis of the Earth points just next door to Polaris, the North Star, and so if you can see the North Star through this little telescope, you know you've got it lined up approximately right. And the motor inside will then guarantee that the camera is turning at 1 revolution in 23 hours, 56 minutes. So a tracker has got batteries feeding a little bit of circuitry, which runs this motor at just the right speed, such that once it's gone through the gearbox, the worm will turn this at the rate of 1 revolution in 23 hours, 56 minutes. What you're paying for, if you want to buy one of these things, and they cost 100 quid upwards, you're buying precision. Unlike the one I built myself, these things are guaranteed to be precise. They are made to relatively high precision, such that when it's operating, once you've got it lined up with the Earth's axis, then it basically will track the stars very accurately. That's how it works. As I say, you plonk it down, usually on a tripod, make sure it's lined up in the right direction, and then you put your camera on here and point your camera in whichever part of the sky you want. So the little polar scope here is used to make sure you've got the tracker lined up. Once the tracker is lined up, you leave it alone and you point your camera wherever you like. You see that some people here have their tracker on a simple ball and socket joint, and you can see that some people use it for taking wide-angle lenses, some people use telephoto lenses. Basically, you can take a huge chunk of sky, or you can concentrate on some object in the distant part of the universe if you so wish. I chose to put my Nikon camera and telephoto lens. I didn't use a ball and socket joint. I prefer this little beastie here, which just makes it easier to adjust where the camera is pointing in the sky. But that's effectively what I use. And I've started this section by saying, why buy expensive equipment when you can use the camera you already have? And that is the camera and lens I already have, because I like wildlife photography. Friends and I have been to Africa a few times. And the last time I was out there, I took this picture of the lion. It wasn't interested in us. It was looking at zebra on the horizon, which is what it was going to eat that evening, probably. And for the last few years, I've been using a Nikon D7500, and I found that a 300mm f4 lens is ideal for what I want to do. In other words, I wanted a lens which is a long enough focal length that I wouldn't have to go up to the lion and pat it on the head before taking its picture. I can take a picture of a lion from a reasonable distance away, but it didn't need to be anything more than 300mm, as I found that gives you a distance of, some 20 meters away from an animal. That's enough that you don't disturb the animal and you can still get a nice picture. And the lens wasn't so big that I found it was so big and heavy, it was a pain to carry around. This particular 300mm lens from Nikon is very lightweight and, as you can see, relatively compact. It's barely 10 centimeters or so long. So I already had a decent camera and I already had a decent lens. If I want to do astrophotography, why would I buy anything else? So I tried using this camera and this lens on a number of different objects. I've also experimented with other focal lengths as well. So let me show you some of the images that I've taken with a camera on a tracker. So although I've told you about expensive telescopes, none of these images were taken with expensive telescopes. So I'm talking about a selection of images taken with that particular camera. Yes, I've changed the camera over the years. The D7500 that I'm currently using, I've had that for a few years. I've gone through other models in the last couple of decades or so. So I am not dissing in any way the people who've decided to buy expensive telescopes. They have produced amazingly good images over the years. You see it if you ever look at astronomy magazines. You see amateurs that are taking absolutely incredible images that are certainly as good as the things that the professionals could have done a decade or so ago. Technology is moving on at such a pace that it is truly amazing what you can do with a telescope. But beware, don't assume that you can emulate what people have spent years building up the experience to do. If you want to use a telescope to do astrophotography, it will take time, it will take effort, and it will take cash. So yes, you have to buy the equipment first, but then you have to learn how to use it and how to use it effectively. Camera on a tracker, it's almost switch it on and go. With more sophisticated equipment, you need to learn how to get the most out of it. So yes, that can be fantastic, but what I'm talking about is not using telescopes here. So let's have a look. Let's just remind ourselves that whenever you take a picture of the sky, it might be disappointing to realize that quite often what you get is that, depending on where you live. In other words, you will probably pick up light pollution as well. Depending on whether you're in a town or a suburb or in the middle of a city, you will probably have street lights around and they will be contributing. You might not think so, but street lights will be reflecting off water vapor in the atmosphere and you will be picking that up when you take a picture. So there's a raw image of a nebula that I was interested in, and you can see the entire background is slightly orange. That's quite common whenever you have any sodium streetlights. These days, most streetlights seem to be LED streetlights, and so the color of the background will be different. But you don't have to worry too much about that because software can mitigate a lot of the problems with light pollution. Not necessarily everything. It's still a good idea to get away from light pollution. It would be great to get the sky as dark as possible before you photograph it. But if you do find you've got light pollution impinging on your images, well, software can do a very good job of saying, well, this background ought not to be orange. It ought to be something a little closer to dark gray, or not necessarily black, but dark gray. And then it can pick out the nebula, again, glowing pink here. You can perhaps see why this particular nebula is called the North American Nebula. Yeah, it actually has a striking resemblance, the Mexican-California line, the Gulf of Mexico, Florida, etc. So, software, some of which is free, some of which you might choose to pay for. Different people have different opinions as to whether or not the free software is great or whether it's worth spending tens of pounds on software that will do the job exactly the way you want to do the job. Again, if anybody's interested, I can point you towards software that will do these sorts of jobs, either stacking star trails or taking images and removing some of the unwanted background. This is a star-forming region. This is a nebula called the Rosette Nebula in the constellation of Monoceros, the unicorn. This is about 5,000 light years away. So light has taken 5,000 years to start from that nebula and reach us here on Earth. These stars are very young stars right in the middle. Those stars have only recently been born. This is recently on astronomical timescales. Remember, our sun is 5 billion years old. These might only be a few million years old, which is very young for a star. So this is effectively a stellar nursery. It's about 5,000 light years away, and it's approximately 100 light years or so in diameter. And this is the sort of field of view you get. Okay, I've taken a rectangle and cropped it down to a square, but this is the sort of field of view you get with a 300mm lens on that camera. And this particular exposure was about an hour or so of a lot of short exposures, a whole set of 30-second exposures. Any that were spoiled, I threw away. Whatever remained, I added them all together. Again, the software that will do that for you, either free software or software you can buy. Notice that not everything that's in the sky, regardless of the fact that you're probing further and further into the universe, this is even further away, this is 7,500 light years away. Just because it's out there doesn't mean you need a phenomenal focal length to get it. Focal length of this one, 85mm. So it's basically just a portrait lens or thereabouts, not far off being a standard lens, and yet you can still pick up detail. This is not a stellar nursery, this is the opposite end of the spectrum. This is a very massive star, which we have good reason to believe is coming towards the end of its life. This is a star called Eta Carinae. Yes. Yes, it wouldn't look quite like this. You would certainly see the star itself, which is very bright. You wouldn't see all of the faint pink stuff out here, which tends to come when you take longer exposures. So this was a 15-minute exposure. So yes, this didn't need a 1-hour exposure. This only needed 15 minutes. But yes, you wouldn't see all of this detail. Remember, the eye is not particularly good at seeing faint stuff, which is why your night vision is generally not good. Humans were built for looking at things during the day and color vision in bright light. Humans were not built to see faint objects. One of the reasons you buy telescopes is to collect more light to give you a better image. So in this particular case, this is large enough in the sky that even a portrait lens of 85mm focal length still gives you a nice looking image. The star itself is embedded right in the middle there, and that star is so unstable, now it's coming to the end of its life. Again, it's been shrugging off some of its outer layers, a bit like our sun is going to do, and all of this nebulosity that you can see there is a result of this star for thousands of years shrugging off some of its outer layers. And we think it's unstable enough that it could go supernova almost any day. That doesn't mean it's going to happen tomorrow. It could be in another 1,000 years. It could be in another 10,000 years. But it looks like it's so unstable, this star is going to go supernova before too long. This is a particular region which I've photographed more than once, simply because I love the colors that are in there. There's an awful lot going on in this particular region. It's in the constellation of Scorpius, one of the zodiacal constellations. There's a very bright star there called Antares. That smudge down there is actually hundreds of thousands of stars in a very tightly packed star cluster. There's another star over here which is illuminating this blue part of the nebula. Again, blue because it's scattering a bit like our atmosphere scatters light and produces a blue sky. And notice there's, again, large areas that are obscured by this dusty nebula. That means that it's obscuring light from more distant parts of the nebula and more distant stars. This whole region is called a cloud complex because there's so much going on. This is one of the closest star-forming regions to Earth. This is only 400 light years away. That's virtually on our back garden, because thousands of light years is what I've been talking about for the other two nebulae. This being only 400 light years away is effectively in our backyard. But after taking this particular image, again with not a particularly long focal length, a 135mm lens, I looked at it and thought, well, would it actually be worth just going in a little deeper into this region, which is really fantastic? So I figured out if I changed to a 300mm lens, it would have a field of view of about that. And a couple of years after I took this image, I returned to this particular target with my lens of choice, the 300mm f4 lens, and took a long exposure of this particular region. And I ended up with this. I was pleased with the sheer amount of detail that was possible to see. Again, we have the star lighting up this region in yellows and oranges. We have this triple star here lighting up this region, giving us this blue reflection. And we have these dark regions as well. And just to make sure we can see all the detail, let's zoom in a little bit. The sheer structure of this nebula, the wispy nebulosity, the textures, the colors, I just find it fascinating that all of this can be caught by a camera and a lens that are fundamentally designed to take pictures in daylight. Nikon didn't build cameras to take pictures of nebulae. They built them to take pictures during daylight. And yet that same technology, when you bung it on a star tracker, can take pictures like that and give you phenomenal detail. Not only individual stars, but all of this material. I was very pleased. It's a fairly long exposure, you notice. 150 lots of 1 minute exposure. So yeah, I basically just set it to 1 minute on its intervalometer, set it to 1 minute and told it to go and just left it taking. And it just took data for 2.5 hours. Luckily, not many of the images were spoiled, so I could use most of those 150 frames of 1 minute each to build up to get that. But the detail, the textures, the wispy structures, the ephemeral structure of this particular nebula, all these dark regions, as well as this rather ghostly looking phantasm coming in at the top, I just think this is a wonderful area in the constellation of Scorpius. But we're not restricted if we decide I'm going to use the camera I've got and I'm going to bung it on my homemade star tracker costing 20 quid or something like that. We're not restricted to photographing objects within our own galaxy. Here's one of our neighboring galaxies. This is the Andromeda galaxy. We're now not talking about hundreds or thousands of light years distance. This is 2.5 million light years away. So light left this galaxy to make this image 2.5 million years ago. It has a couple of satellite galaxies. These small smudges here are not thumbprints. They are genuine satellite galaxies of the Andromeda galaxy. 2 million light years, 2.5 million light years might sound like a lot, but this is our immediate neighbor, galactically speaking. It's so close, we are gravitationally pulling on each other. And in fact, it's coming towards us because it is close enough that the gravity of the Milky Way galaxy and the gravity of Andromeda are pulling these two galaxies together, and they will eventually collide with each other. Again, not for quite a while, don't worry. But it is nice to know that one of our closest neighbors is big enough in the sky, and you probably don't appreciate this, but the Andromeda galaxy itself is much bigger than the full moon in the sky. It's fainter than the full moon, but in terms of how big is it, well, the full moon you can easily cover with your thumb. But this is something like 6 full moons end to end. It is a big object, but because some of it is quite faint, it's quite bright in the middle, and you can see that with the naked eye, but the outer parts are rather faint, and they are more difficult to see, but you can photograph them. One advantage of photographing something like this is even though the middle is much brighter than the edges, by doing some image processing, you can bring out the fainter parts of the galaxy and make it a little more balanced to show you what you would see if your eyes were more sensitive. But that's by no means the limit either. 2.5 million light years, that's easy. How far can we go? Here's a collection of galaxies called Markarian's chain, a whole load of galaxies, and again, we can zoom in to see a little more of what's going on. Each galaxy, we can see individual structure in the galaxy. We can see definitely spiral arms. Some of the background is coming out a little mottled, never mind. And we can zoom into individual galaxies. This particular one seems to have spiral arms that aren't coming from the middle, but the spiral arms are starting from a bar that seems to be going through the middle of the galaxy. And the more we look, the more we realize each of these galaxies as individual structure. That one seems to be a bit fluffier than the others. It's so-called flocculent spiral arms. And if we look at some of the galaxies, they are close enough that they are pulling on each other. And again, the one galaxy is actually raising tides on the other galaxy, like the moon raises tides on the Earth. These are close enough that this galaxy is being disrupted by the presence of its neighboring galaxy and producing those structures there, a sort of distorted spiral structure. This is 50 million light years away. So basically, the light left this galaxy cluster when dinosaurs were still roaming on the Earth. But that's not the limit. Who remembers 2020 when we had lockdowns? Yeah, right. Yep. So in July of 2020, I couldn't go to the pub and see my friends, so I thought, what can I do? Let me try and figure out what is the most distant object I can possibly catch with my Nikon and 300mm lens. It's not that bright blob in the middle there, that just happens to be a star. I looked up a survey of galaxies and said, right, if I'm going to put my camera and telephoto lens on my little tracker there, what's the most distant object I have a chance of catching in July of 2020? In July, of course, we're in the middle of summer, night doesn't last very long. If you wait till it gets dark, you've only got a couple of hours before dawn twilight starts. So you've only got about 2.5 hours of genuine night. So I tried to find an object which was high enough in the sky that I could catch that. And I looked in a survey that said, well, there's a star there, which is a 5th magnitude star. There should be a very interesting galaxy in the middle of that square. This particular galaxy has got a very bright nucleus. It's a particular type of galaxy called a quasar. And quasars are galaxies which have a very bright nucleus, so bright they can be seen from enormous distances. So I figured that if that galaxy is there, I wonder if I can possibly pick it up with my camera and 300mm lens. So that's what I did, the same camera, the same lens, and here I took about 2.5 hours worth, 256 images of 30 seconds each. I didn't sit and watch it, I just set it up and then told it to take 30-second exposures, then went back indoors again. Yes, clouds came and went, so some of the images I took were wasted. Also, my neighbor has got a security light, which means when a cat walks in front of it, the security light comes on. And this was taken within 10 meters of a street light. So I still had to make sure the camera was pointing in one way, and hopefully the street light didn't get into the camera lens and spoil the image. So I took my 2.5 hours worth of imaging and produced this 20 megapixel image, and I figured that hopefully what I want is in the middle of that square. So once I'd finished processing it, I zoomed in and said, well, it should be in the middle of that square. And that is it. That is the least impressive image you're ever going to get shown in this room, I would imagine. So the light from this quasar was effectively focused into 1 pixel. Let's blow it up. That's it. That's what I was interested in. 1 pixel. Feel like I ought to submit this for a calendar competition, just the single pixel from the middle there. So yeah, some light perhaps has spilled out into the neighboring pixels. I've artificially brightened this so you can see some of the other pixels. There's some stars in the background, but I am absolutely confident that that is the galaxy I was interested in because I absolutely double-checked its coordinates against known coordinates that people had already checked. So it's only 1 pixel or so of the 20 megapixel image. But it's not the fact that that's a spectacular image. It's the fact that you can catch it at all. Because the light that produced this smudge there, this pixel, this galaxy is at a distance of 25 billion light years. Not million, 25 billion light years. How long did it take the light to reach us? Approximately 12.4 billion years. The universe is only 13.8 billion years old. So this light had been traveling from this galaxy to my camera for roughly 90% of the time that the universe has existed. In other words, the universe was only 10% of its current age when the light left. And it's taken 12 billion years to get here. For half of its journey, the Earth didn't even exist. After about 8 billion years of travel, the sun came into existence. The Earth came into existence. And for the last few billion years, it was traveling on. For the last few million years, it came into our galaxy. And then it finally arrived in England, dodged a few clouds, and bam, hit the sensor and produced a few photons. The universe we know is expanding. And that means the more distant an object is, the faster it's moving away from us. And at that incredible distance, because of the expansion of the universe, which is something that we know how fast it's expanding, we can calculate that at that distance, this galaxy is actually receding from us at twice the speed of light. And that really takes some working out, because most people will say, hang on, it can't. No. If it's receding from us faster than light, how can the light ever reach us? And yes, that sounds paradoxical, but it simply means that our brains are not wired to think about what's going on in an expanding universe. It is right, and if you're interested, I can send you a link that tells you how the light can reach us, even though the object itself is moving away from us at twice the speed of light. In a sense, the light is trying to get to us, but is being dragged backwards. It's a really weird situation that we're not used to thinking about, because on the day-to-day level, we never encounter this sort of thing. But although that is the least impressive image, in many respects, it is the most impressive image. The fact that you can actually pick up a dot from a galaxy 25 billion light years away using a camera that's designed to take pictures in daylight. Astrophotography is not something for which you need astrophotographic gear. You can use the camera you've already got. Let me just finish by reminding you that it's great occasionally to go on holiday, and although I like taking images of wildlife, I like watching wildlife with binoculars, I like astronomy, i.e. using binoculars to look at the sky. And of course, with the camera, we can do wildlife photography and we can do astrophotography. Wildlife overlaps with astronomy because if you go to Africa to look at the wildlife, you're also getting away from streetlights. Because if you go to somewhere in the middle of Kenya or Tanzania, you might be 100 miles from the nearest streetlight. So the dark skies are phenomenal. So the idea of going on safari, which friends and I have done from time to time, that gives you the overlap between wildlife and astronomy and photography. So basically, you can look at and photograph animals by day, and you can look at and photograph the stars by night. Whatever. Sleep when you get home. There's no point in wasting good holiday time when you can be doing one or other of those. So with something like that, a little tracker doesn't add much to your sort of overnight luggage. You know, it's about a little less than a kilogram or so. So putting a tracker and taking it with you is easy enough. This just shows you what you see when you look through that polar scope to make sure you're lined up on the Earth's pole. Polaris is not quite at the pole. Polaris is slightly off to one side, and this app will say, well, I know where you are and I know what the time is. So if you are correctly lined up on the pole, Polaris should appear where this dot is. So you simply nudge your tracker until that's where Polaris appears, and Bob's your uncle. Everything is nice and easy. But that is easy enough from England, because remember, the North Celestial Pole is directly above the Earth's North Pole. So from the latitude of England, it's very easy to see where the pole is. It's sitting up there 50 degrees above your northern horizon. But if you go to Kenya on the equator, where's the pole? Well, it's on the horizon and behind an elephant or something. So you can't actually see the North Pole, and you can't see the South Pole either from the equator. The equator is probably the worst place to do astrophotography. But given that Kenya is so wonderful for wildlife, I have been there a few times. And effectively, I've had to guess where the pole is because I can't actually see it with my tracker. But it's still possible to take nice images. And as well as taking images with a telephoto lens, I've also tried wide-angle photography and tried to cover a larger swathe of sky. So from England, on a dark night, you might see the Milky Way running across the sky. And if you're lucky, you can see some of the brighter parts of the Milky Way. But if you get somewhere where there's no light pollution, then the amount of detail your eye can pick up in the Milky Way is absolutely phenomenal. You can see all of these, not only the brightest part, that's the center of the galaxy, you can see all of this area, and you can see the dark dust lanes obscuring some of the light from more distant stars. And of course, if you take a photograph of it, your eyes aren't sensitive to color at night, but if you take a photograph, then you can start to bring out colors as well. So that, as you can tell from the corners, is a mosaic taken with a wide-angle lens and then mosaic together to give me a slightly wider angle. If we zoom in and just highlight, that might be a bit suspicious, that very bright star there. That isn't a star, that's Jupiter. And over here on the left-hand side, that's Saturn. And if we wanted to, we could start to zoom in and see all of these little blobs in there, because all of these blobs are nebulae or star clusters. One of those, for instance, is the pillars of creation that we were looking at before. So you can appreciate wide angle, you only get a few pixels in your nebula. Telephoto, you can make a lovely image of it. But in this particular case, there are loads of star clusters and nebulae that in principle you can sit and look at on your computer monitor and zoom in to see what it is you've caught. You can use a star atlas, or you can use an app on your phone to tell you what's going on in the background. You might look at that and say, well, there are lots of interesting objects on there. They're given particular catalog numbers when you look them up in atlases, etc. And you might say, well, it looks like all the interesting stuff is in the top half and there's nothing interesting going on down here. Well, not true. These are labeled according to Charles Messier, who was an 18th century French astronomer. And from France, you can't see that far south. Therefore, he mapped out a whole load of objects that he could see, and he stopped where his horizon was. And therefore, when you go to the equator, of course, you can see further south, and you can see more than Charles Messier saw in his 18th century days. But I guess the message to leave you with is star trackers are amazing. mainly because it's not the trackers themselves, it's the fact you've already got a good camera. And maybe you've got one or more fantastic lenses. And a tracker like this might cost 100 quid or more, or you can build one yourself if you want to follow these instructions. You can build one for about 20 quid or so. If you decide to use a tracker, they don't weigh that much, 0.5 kilogram to 1 kilogram or something like that. If you're going on holiday somewhere where you're going to get away from streetlights, and you're going to take a camera because you're interested in taking pictures of whatever it is you're going out to see, why not put a camera tracker in your luggage, and then you have the opportunity, if you have clear skies, to take pictures like that. So you can do astrophotography without ridiculously expensive equipment. Thank you very much.